Imagine, just for a second, that you are a teacher. But, not just any teacher. You have four of the world's most powerful, multi-billion-dollar AI models just sitting right there in your classroom.
Get the lineup.
Right. And you decide to give them all the exact same math homework, like a 2,000-year-old math problem.
Mm.
But because this is the future, obviously, you don't just want the answer scrawled on a piece of paper. You actually want them to build a modern, fully functional software application to solve it.
Complete with a graphical user interface and everything.
Exactly, a full Tkinter GUI in Python.
And crucially, you aren't going to hold their hands through the process. You just give them a strict set of architectural blueprints, walk out of the room, and basically see what they manage to compile.
And that wild scenario is exactly the premise of today's deep dive. We are unpacking this fascinating comparative software test that basically evaluates four heavyweights. We're talking ChatGPT, Claude, Gemini, and Grok.
All trying to solve the exact same problem.
Right. The challenge was to design, debug, and test a Python program to calculate the exact value of pi. So our mission today is to uncover the unique successes, the honestly kind of bizarre blind spots, and the, well, highly distinct personalities that each of these AI models exhibited when they faced identical constraints.
And for you, the listener, understanding these differing behaviors is just, it's an absolute necessity today.
Oh, for sure.
Because whether you use AI to write production code or analyze complex data sets or, simply just automate your daily workflows, knowing how these specific models fail or succeed at a rigid multi-step logical task gives you a massive advantage.
It really does. It tells you exactly which tool to trust for your own projects. And honestly, more importantly, it shows you the specific blind spots where you need to step in and serve as the ultimate quality control.
Exactly. You have to know what to watch out for.
Okay, let's unpack this. Because before we get into the wild ways the AIs actually behaved, we really need to understand the obstacle course they were running. The math homework itself wasn't just, find pi.
No, it was much more specific.
Right. They had to use Archimedes' geometric approach from 250 BC.
Right. So Archimedes realized that you could approximate pi by placing regular polygons. So think of shapes like hexagons or octagons, placing them both inside and outside a circle.
Okay.
And if you have a circle with a diameter of exactly 2, the perimeter of the inscribed polygon, so the one fully inside the circle, that gives you a lower mathematical bound for pi.
I see. And then the one on the outside.
The circumscribed polygon, yeah. That one on the outside gives you an upper bound.
So basically, as you increase the number of sides on those polygons, they start to look more and more like a real circle.
Right, exactly.
So the upper and lower bounds just kind of squeeze together tighter and tighter around the true infinitely long decimal value of pi.
That's the core concept. But the prompt didn't just let the AI models pick an arbitrary number of sides to draw. It gave them a very strict, highly specific exponential mathematical formula.
Right, this is where it gets tricky.
Yeah, the number of sides, which is represented by n, it had to equal 6 times 2 to the power of k minus 1.
Okay, hang on. Let me run that through my head. So n equals 6 times 2 to the power of k minus 1. And the user running the software gets to input the value of k, which the prompt defined as a multiplier varying from 1 to 20.
That's right.
Okay, let me just do the math on that real quick. If a user maxes out the software and enters a k value of 20, that's, 2 to the 19th power times 6. Meaning the software is calculating the precise geometry of a polygon with 3,145,728 sides.
Yeah, over 3 million sides.
That is wild.
So now you can really start to see the hidden traps in this prompt. It's intense. But believe it or not, that was only the first phase.
Oh, right, the revision phase.
Exactly. The models were then put through a second iteration where they had to calculate 3 specific Pythagorean means of those upper and lower bounds.
Which were the arithmetic mean, the geometric mean, and the harmonic mean, right?
Yeah.
Now, I know the arithmetic mean is just your standard average, right? You just add them up and divide by 2.
Hmm.
But why add the geometric and harmonic means? Like, what does that actually do to the calculation?
It's a great question. It essentially acts as a mathematical smoothing mechanism because when you are dealing with geometric approximations of circles using straight lines, the upper and lower bounds don't actually converge at the exact same rate.
Oh, interesting.
Yeah, the arithmetic mean might slightly overestimate the true value. So the geometric mean, which involves multiplying the bounds and taking the square root, and then the harmonic mean, which uses the reciprocals of the numbers, they sort of weigh the extremes differently.
I see.
By calculating all three, you get a much tighter, much more nuanced approximation of pi than any single bound could ever provide.
That totally makes sense.
Yeah.
It's almost like using 3 different types of camera lenses to focus an image until it's just perfectly crisp.
That's a really good way to think about it. But then the prompt threw one final wrench into the gears.
It always does.
The AIs had to compare their calculated means against Python's stored IEE 754 floating point pi.
Okay, wait. Why that specific standard? What is IEE 754?
Well, because computing geometry with 3 million sides really pushes the absolute limits of binary arithmetic. You see, computers don't handle decimals the way our human brains do.
Right.
They use the IE 754 standard to allocate a very specific number of bits to the decimal's fraction and exponent. So when you subtract two numbers that are almost perfectly identical, which is exactly what happens when your upper and lower bounds are squeezed together by 3 million-sided polygons, you encounter something called catastrophic cancellation.
Catastrophic cancellation? That sounds terrible.
It is for a computer. The system basically runs out of bits to store the microscopic differences, and suddenly rounding errors just explode.
Wow. Okay, so this wasn't just a math test at all. This was a brutal system stress test.
Absolutely.
The AI literally has to juggle complex geometry, exponential math scaling up into the millions, visual Tkinter GUI layout, and extreme floating point precision limitations all at the exact same time.
All simultaneously.
It's like giving 4 master chefs the exact same ridiculously complex recipe for a multi-layered pastry. We aren't just judging if the final cake tastes good, we're judging how messy they left the kitchen.
Oh, sure.
And how they plated the dessert, and honestly, whether they remembered to turn the oven off before the whole house burned down.
And as we dig into the results here, you're going to see that some of these chefs left the kitchen in a complete state of disaster.
Let's start with the model that actually seemed to understand it was cooking for a human being. Because when you look at the illusion of the perfect user, ChatGPT and Claude had radically different philosophies.
Completely opposite, yeah.
ChatGPT kind of played the role of the iterative refiner.
It really did. ChatGPT did remarkably well in anticipating the human element of software. For instance, in its initial design, it proactively added an approximation quality metric to the GUI.
Which was definitely not in the instructions.
Exactly. The prompt didn't explicitly ask for this at all, but ChatGPT understood the underlying intent of building a user interface, which is making raw, complex data comprehensible to a human brain.
So it basically provided a qualitative summary for the user.
Right. But where it really shined was in building safety nets. It anticipated edge cases beautifully.
Tell me about that.
Well, if a user entered a K value of 0, or say 21, which obviously exceeds the maximum limit of 20, or even if they typed in a decimal like 3.5, ChatGPT had actually programmed specific pop-up dialog boxes to intercept those exact errors and warn the user.
Okay, now let me push back a little here, because adding error handling pop-up boxes kind of feels like software development 101 to me.
Sure.
Like, is it really that impressive that an advanced billion-dollar AI remembered to catch bad inputs? It feels like the absolute bare minimum you'd expect from any coder.
Well, you're not wrong. It is the bare minimum for an experienced human developer. But you really have to remember how large language models are actually trained.
Okay, how so?
Their training data is filled with billions of lines of perfect, theoretical code snippets designed just to demonstrate a concept. So because of this, AI models frequently assume what developers call a happy path.
A happy path?
Yeah. They assume the user will behave perfectly and input exactly what is expected.
I get it. They write code for a perfect world.
Precisely. So to break out of that theoretical mindset and actually anticipate the chaos of a human randomly typing 3.5 into an integer field that shows a much higher level grasp of actual application deployment.
Because it recognizes that a script running in a vacuum is totally different from a tool in a real user's hands.
Exactly. Now, to be fair, it wasn't completely flawless.
Right.
During the revision phase, when the prompt asked it to add those Pythagorean means we talked about, it initially failed to output a single distinct value for each of the 3 types.
Oh, so it just kind of lumped them together.
Yeah, requiring the user to actually prompt it again for a fix. But overall, it really embraced the messy human element.
Okay, so ChatGPT assumed the human user was flawed and built safety nets. But what happens when an AI doesn't just build a safety net, but basically locks the user in a straitjacket so they can't even touch anything at all?
Oh, boy.
Because that is exactly what happened when Claude took over the architecture.
Yeah, Claude's approach to the user interface was fascinatingly restrictive. Instead of using a normal text input box for the L multiplier like all the other models did, Claude went out of its way to design a visual slider, hard-locked from 1 to 20.
Which, I mean, looks very sleek and modern, sure, but it completely defeats the purpose of stress testing software.
Right, because you can't break it.
Exactly. If I'm the developer testing this application, I want to input a 21 just to see if the engine catches fire. But Claude physically blocked the user from testing edge cases outside those bounds.
It absolutely prioritized aesthetics over functional testing. But the structural restrictions didn't just stop at the graphical interface.
No, they did not.
Claude suffered from this bizarre form of version control amnesia.
That's a great way to put it.
When it was prompted to iterate and revise the code, unlike the other models that just appended the new code to the visible chat history, Claude entirely overwrote its initial program.
It provided zero revision control.
None.
The user had to literally make Claude recreate the underlying code from scratch just to get back to a working state.
Yeah, it's brutal.
It is exactly like hiring a contractor to build your house. And when you ask for like a slight tweak to the kitchen layout, they don't just change the blueprints without asking. They actually gather up all the old drafts and burn them in the front yard, so you have no historical record of the project whatsoever.
It's incredibly frustrating for a developer. I mean, version history isn't a luxury, it's an absolute necessity.
Totally.
But honestly, the most glaring architectural hallucination came during the revised design for the Pythagorean means. Claude unexpectedly decided to split the program into two entirely separate Python files.
The two-file disaster.
Yes.
It created a pylogic.py file and then imported that into a pycalculator.py file. Why on earth would it do that for a simple math script?
Because Claude was basically trying to emulate enterprise-grade software engineering.
Oh, I see.
Yeah, in massive software projects, separating your core mathematical logic from your user interface is actually a best practice. It's called modularity.
Right.
It allows different teams to work on the visual front end and the mathematical back end without stepping on each other's toes.
But no one asked for a multi-team enterprise architecture. This is a single script for a test.
Exactly. This is a perfect example of an AI hallucinating complexity based on its training weights.
Wow.
Claude has ingested massive GitHub repositories, where the highest-rated, most robust software is highly modular and spread across multiple files. So it falsely associated the prompt's request for a robust GUI application with that complex multi-file structure.
So it basically over-engineered the invisible architecture. It tried to build a skyscraper when we just asked for a tool shed.
Very much.
And as a result, the user experience degraded into total confusion because of these unnecessary program dependencies.
Right. Claude overcomplicated the invisible structure. But what happens when a model struggles with the visible structure and, well, the core mathematics?
Oh, man.
That brings us to the friction between spatial layout and strict logic, which was just painfully evident in Gemini.
Gemini really fumbled the math here.
Yeah.
We established that the core of the assignment was the exponential k multiplier, right? That n equals 6 times 2 to the power of k minus 1.
Yes, the Archimedean formula. And in its initial design, Gemini was actually the only model that outright ignored the k multiplier logic.
Just totally skipped it.
It simply allowed the user to input the number of polygon sides directly, entirely bypassing the formula we gave it.
Wow. And then when it was forced to use a multiplier in the revised design, it completely abandoned the exponential nature of the formula anyway.
Right. It interpreted k as a simple linear multiplier, calculating the sides as just n equals 6 times k.
Which is a catastrophic mathematical failure in this
It
context.
completely breaks the assignment.
Let's do the math on that again, just to put it in perspective. If I input the maximum k value of 20, the Archimedean formula we talked about earlier dictates the AI should calculate geometry for over 3.1 million sides.
Right.
But if Gemini uses its flawed 6 times k formula, 6 times 20, that's 120 sides.
Yeah.
It's off by over 3 million. So is Gemini just hallucinating the math here, or is it actually taking the lazy way out because exponential scaling is computationally harder to pull off?
Well, it's highly unlikely to be a computational limitation on Gemini's end. This looks like a classic failure in prompt adherence.
Okay, meaning what?
Meaning Gemini likely parsed the prompt, locked onto the specific word multiplier, and then defaulted to the most common simplistic interpretation of that word, which is just linear multiplication.
Oh, I see.
It failed to synthesize the strict multi-step constraints of the Archimedean exponential method. It just missed the context entirely.
But the struggles didn't just stop at the underlying math, did they? Gemini also tripped over the visible interface, the Tkinter layout itself.
Yeah, it was a mess. Gemini required a full iteration specifically because of, well, a slight mix-up between how layout managers handle space.
Let's unpack that.
So in Python's Tkinter library, there are layout managers like pack and grid that dictate exactly where buttons, text labels, and input fields sit on the actual screen.
And mixing those up usually results in a chaotic, broken interface where buttons just overlap or disappear entirely.
Exactly. And humans design GUIs visually, right? We look at the screen and we drag things around until they look right. But AI models are generating these interfaces entirely through text.
Which have to be incredibly difficult.
It really highlights a profound and known weakness in large language models. They have a severe lack of spatial awareness.
Because they don't have eyes.
Right, and AI does not see the screen. It has no conceptual model of visual space at all. It only understands tokens and text.
That makes a lot of sense.
So when it tries to organize a grid coordinate system for a user interface, it is essentially trying to paint a picture in the dark using only mathematical descriptions. Gemini got its spatial logic all tangled up simply because it couldn't visualize the layout manager's parameters.
So Gemini struggled with how things looked and fit together on the screen.
Yeah.
But our final model, Grok, went in the exact opposite direction.
It really did.
Grok proved to be the absolute front-end designer of the group.
Grok absolutely excelled at the visual presentation. It generated the most aesthetically pleasing and logically arranged GUI right out of the gate.
I mean, it did have a minor spatial quirk initially, didn't it?
True.
It included so much rich information in the display window that the user was actually forced to scroll down just to see all the results.
Yeah.
Like, it didn't size the default window appropriately for the sheer amount of data it was generating.
It was a minor spatial miscalculation, yeah. But by the revised design, Grok had refined this perfectly. The GUI was explicitly described as clean and clear. But the most impressive aspect of Grok's visual design was its extensibility.
Okay, explain what you mean by extensibility in this specific context.
So extensibility basically means the software was designed with enough structural foresight and spatial room to actually accommodate future additions easily.
Got it.
When the prompt asked Grok to add the new arithmetic, geometric, and harmonic mean calculations, Grok's GUI easily absorbed that new data without the user having to manually readjust the window sizes or rewrite the whole layout manager code.
So it basically anticipated that the software would grow over time.
Yes.
That's fantastic software engineering. But there is a catch.
There's always a catch.
Just like Gemini, Grok failed to implement the correct formula for the K multiplier. It totally dropped the ball on the fundamental mathematical logic at the heart of the prompt.
It prioritized the visible structure over the invisible mathematics.
Right, so Grok is essentially the high-end architectural designer who builds you a stunning, beautifully spacious, highly extensible house, but completely forgets to hook up the plumbing inside the walls. The house looks amazing, but the water doesn't run the way the blueprints explicitly stated it should.
That is a perfect analogy. However, if we look at it from a long-term software maintenance perspective, Grok's extensibility is still incredibly valuable.
How so?
Well, if you are a developer, it is generally much easier to dive into the code and just fix a single line of mathematical logic than it is to completely tear down and redesign an entire user interface from scratch just because it was built too rigidly to accommodate new features.
Okay, that's a really fair point. So let's step back and synthesize what we've uncovered here today. Because we gave 4 cutting-edge, state-of-the-art AI models the exact same set of blueprints, and they behaved like 4 completely different software engineering teams.
The evidence makes it undeniably clear that today's AI models are just not interchangeable monoliths.
Right.
They have highly specific architectural paradigms, unique strengths, and glaring weaknesses based entirely on how they process constraints.
So let's just run down the list for the listeners. ChatGPT acts as the iterative UX refiner. It assumes the human user is going to make mistakes and actually build safety nets to catch them.
Which is great for user experience.
Yeah. Then Claude plays the role of the overeager enterprise architect. It attempts this complex professional-grade modularity, splitting files and restricting inputs even when that complexity actually breaks the user experience.
A classic case of over-engineering.
Totally. Then you have Gemini, which is essentially the erratic junior developer. It requires significant hand-holding on strict mathematical logic and really struggles to comprehend the spatial reality of a UI layout.
Because of that lack of visual awareness.
Right. And finally, Grok is the pure front-end designer. It prioritizes a clean, extensible, visually appealing interface, but occasionally lets the core mathematical equations slip through the cracks just to achieve that polished look.
Which brings us to the ultimate, crucial takeaway for you, the listener. As AI becomes more and more integrated into our daily workflows, you absolutely cannot afford to be a passive consumer of its output. You have to act as the ultimate project manager.
Meaning you absolutely cannot just blindly copy-paste AI code, compile it, and assume the job is magically done.
Never. You are the final quality control layer. You have to verify everything.
Because they all have blind spots.
Exactly. You have to run the math to check if the AI quietly replaced your complex exponential formula with a lazy linear multiplier. You have to physically execute the code to see if the Tkinter layout actually renders properly on a real physical computer screen, rather than just trusting the AI's textual description of the layout.
Right.
And maybe most importantly, you have to aggressively maintain your own version control and backups just in case your AI decides to wipe your previous working drafts entirely out of existence.
Basically, you have to inspect the kitchen before you eat the cake.
Always.
Which leaves us with a final, pretty fascinating thought to mull over. You know, when we prompt an AI to build something today, we tend to think of it as a neutral translation engine. We input human intent, and it just flawlessly outputs machine code.
But as this Pi experiment clearly shows, that's just not true at all.
Not even a little bit. These models have distinct coding philosophies. They prioritize very different things based on their training. So the next time you fire up an AI for a big project, remember you aren't just selecting a neutral software tool, you're essentially hiring a technical co-founder.
That's a scary thought.
It is. And the real question is, have you checked if your new AI co-founder's coding philosophy actually matches the project you were trying to build? Because if you don't, you might just end up with a beautiful house that has absolutely no plumbing.